No, that's just that worksheet I gave you with those 4 reactions. No, you don't need to turn that in.
It's just for practice.
Yeah, that's practice. So I'm going to, as often as I can, I'm going to have an in-class something that you, and we might not finish it. You can take it out with you and finish it. It's practice. Okay, this is kind of where we left off yesterday. One thing I didn't mention with hydrogenation, like this reaction right here is hydrogenation. How can you tell that? You're reacting it with hydrogen. This nickel right here is a catalyst. And so if we were reacting that with hydrogen, there is a catalyst, and that it's either nickel, platinum, or palladium, or you usually see a catalyst there, and it's not very much. 3, 4, 5 parts per million of those metals they're very, very potent catalysts. I don't know about nickel. Maybe you need a little bit more than that, but platinum is a very potent catalyst. Bromine, the second one, you're going to get a bromine here, and you're going to get a bromine here. But let's look at this one. So let me just see what we have here. Okay, all of those lines are hydrogens, and we're going to add water to this molecule. So, what product are we going to get? Markovnikov's rule tells us, what does it tell us? So the hydrogen is going to go to the carbon with the most hydrogen. So here's an H, OH. Look at this carbon here. This carbon here has no hydrogen on it. 0. This carbon has 1. So the hydrogen is going to go to that carbon. You with me? Okay, so we're going to get, so this is going to get us down to here. We're going to get 2 hydrogens here. We're going to have this methyl here, and we're going to get an OH. There's our water. All right? So the hydrogen goes to the carbon with the most hydrogen. And you can see you can get different kinds of situations. Here's one where one carbon has 1 hydrogen and the other carbon has no hydrogen. So it's going to go to that one with the 1 hydrogen. On D, we're going to add HCl to D. Where is the Cl going to go? Carbon with the least amount of hydrogen. Which carbon is that?
On this?
Yeah, on D. The CH. So the chlorine is going to go here, and the other hydrogen, the hydrogen is going to go there. And we're going to get rid of that double bond. So we're going to get a compound like this. Okay. And those are, there they are, but they've put them in line, they've put them in line formulas there. But that's the products. Okay, polymers, plastics. Where do plastics come from? And folks, plastics are all around us. The water bottles, that box right there is all plastic. These markers are plastic. Half of your car is plastic. Your bumper, all kinds of plastics, all over the place. Homes are insulated with plastic, polystyrene, often. Ziploc baggies, milk cartons. So where do they come from? They're all coming from crude oil. Basically, crude oil is your starting material. You're getting things out of crude oil and sometimes doing some chemistry or something to rearrange things and get the monomer that you want. You're making polymers. Many monomers. What is mono? One unit. You take the individual unit and link it to itself many times, and you get a polymer. Yeah, let me show you how this happens. Here's a little diagram. Let's just use the simplest molecule here. I'm going to draw these hydrogens right up like here. Here's ethylene. So this is ethene, or its common name, which we just learned a minute ago, is ethylene. And let's take another one right next to it. You don't really need to write out these reactions per se. I just want you to see how this proceeds. This is our monomer. That is a monomer. That's the individual unit, ethene. And so what they do is they get a free radical of some sort, generate one. This is the initiator. This starts the reaction. And just think for a minute that you've got an electron here. Boy, that looks like an emoji, doesn't it? There's another one. You have to look up the list of emojis to see if they have that one. Doesn't. We'll get it patented. So this free radical comes slamming in to this molecule. Huh, doesn't erase. What's wrong? Okay. So this electron comes in here, that electron comes in here, and you form a bond. And that generates the free radical right there. It moves that unpaired electron. That's what a free radical is, an unpaired electron, right to there. And so this electron comes in to form a bond, and it moves that free radical, that unpaired electron right there, and it happens again, and it just keeps happening again and again and again. And so what does it look like now? Well, you got this R on the end of it. It looks like this. There's your first ethylene. There's your second one. There's your third one. There's your fourth one. And it goes on and on and on. And so what it is this. That's polyethylene. What does N equal? It depends. N can be 100, it can be 1,000, it can be 10,000. And this is now many ethylenes. Polyethylene. And that's Ziploc baggies. That's how you make Ziploc baggies, right there. I had an opportunity to, I don't know why, I lived in this city where they made Ziploc baggies, Dow Chemical Company, and they gave tours every so often to show how they made polyethylene and blew it into a film and then turned it into bags and all that sort of stuff. Garbage bags, sandwich bags, bags, trash bags. This is,
What's the reactor?
DR?
Yeah.
I'm not sure. It might be it might be methyl chloride, something like that. Something that they could kick this off and form a free radical. So it might be this. You can't get a bottle of that. You have to generate it. You have to somehow get a molecule that will break down into two free radicals, and that gets it going. This is a very hot reaction. You have to control this. You can melt the kettle doing this reaction. You can blow something up if you do this reaction. So once this gets going, it gets hot. So they have to do it at a certain speed that they can handle the heat that's being produced. So there, you take 2-methyl-1,3-butadiene. I think this was one of your things. You polymerize it and you get rubber, like to make automobile tires, by polymerizing isoprene. You get rubber. That's its common name, rubber. There's nylon. Don't worry about nylon. That's a different reaction. Okay. What do we got over here? We don't have ethene. We have tetrafluoroethene. Instead of hydrogens, the monomer is a carbon-carbon double bond with 4 fluorines on it. You polymerize it, you get polytetrafluoroethylene, or Teflon. That's Teflon. That's how they make Teflon. Pardon me?
What are they doing?
Polymerizing it. Polymerizing. Doing just what, just, yeah, so that's your monomer, and you do that 100 times or 1,000 times, you have 1,000 of those units. It would be 2,000 carbons long, because it'd be 1,000 monomers. That's Teflon. Okay, now, this is a handy little chart right here. If you look at the bottom of your water bottles, or if I look at the bottom of my water bottle, you're going to see PE, well, what are you going to see? Hunt for, somewhere on there, you should find a little triangle. There it is. I found it right there. There's my little triangle. It's got looks just like that. The number 1 with arrows going around in a triangle, PETE, polyethylene terephthalate. That's the plastic that this bottle's made out of. Made out of polyethylene terephthalate. Here's your high density polyethylene. Here's your low density polyethylene. So low density is your sandwich bags. High density is your milk cartons, milk jugs, a little bit firmer. What does that mean? N is bigger. This might have, I don't know the number. I'm going to just guess. Maybe this has 400 units in a row of ethylene, and that might have 800 or 1,000. It's high density. Polypropylene. Instead of that, this being your monomer, you've got a methyl group hanging down every other carbon. So that you have this, you have a carbon with a methyl, carbon with a methyl. That's your propylene. Your propylene unit. Here's home insulation, polystyrene, or the white polystyrene cup, or the cooler you take to the picnic. That's polystyrene. That's the monomer. All right, so every plastic has that. Other is different stuff. Polycarbonate falls in this class. This is the one that 5 to 10 years ago, they said stop using that plastic for baby bottles, for microwavable containers. Why? Because they give off bisphenol A. Number 7. Right? So if you go home and you have plastics you're putting in the microwave, Well, I wouldn't put plastics in the microwave. Put it in bowls. Put it in glass jars or glass containers rather than plastics, because you're heating all this up, and it can leach some stuff out of the plastic into your food. So some plastics are better than others for doing this, but in the other category shouldn't be used for food. Okay? That other category.
So, Claire, what's the one that
Tupperware?
what's that made out?
Probably high-density polyethylene, I'm not sure. It might be a form of that. I would think it's high-density polyethylene. I'm not sure. Okay, aromatics. Are ring structures that have multiple double bonds. The most common is benzene. This is benzene right here. Aromatic, these things had a aromaticity. They had a fragrance or odor. I wouldn't always call it a fragrance. Benzene actually is a carcinogen. But oil of wintergreen, it does have a fragrance. So candy, chewing gum has oil of wintergreen on it, or methyl salicylate, vanilla. Straight chain compounds are called aliphatics. So, this is an aliphatic molecule. Aromatics are not aliphatic. They're cyclical. They're not in a chain form. They're in a ring. Okay, well, I'm not going to dwell on this. This chemist Kekel got really into this. What's the molecular orbitals look like? But I'm not going to dwell on that. Okay, it does not matter how you draw this. You can see you can draw it with a double bond, single, double, single, double, single. Or you could start single, double, single, double, single, double. The important thing is they alternate. Don't put two double bonds next to each other. They're alternating double bonds. And because it has two different ways of drawing it, we say these are resonance structures. There's two identical ways of drawing the benzene using single and double bonds. What the reality is this. We're not going to draw it this way. The reality is that let's pretend we're working off of this one. That double bond there is delocalized around those two. This double bond is delocalized around those two. And this other double bond down here is delocalized around in there. So really, the way we draw this is we just draw a circle in there. Instead of we can just draw a circle inside the ring. So that's benzene. This is cyclohexane. Right? No ring in there. It's an alkane. A ring inside the six-membered circle there is benzene. It's aromatic. Cyclohexane is not aromatic. It's a saturated hydrocarbon. This is an unsaturated hydrocarbon, but it's going to behave differently than just a normal double bond. It's got alternating double bonds. So it's in a class of its own. It's an aromatic hydrocarbon. And here's what Kekel got into. These electrons that are being shared between get delocalized into a pi cloud above and below the ring. You get this place where these electrons can be found. And you get this little cloud area above and below the ring. overlapping orbitals. We're not going to get into that. But here are all, those are all benzene. Those are all appropriate ways of drawing benzene. All right, whether you put the alternating double bonds or whether you put the ring, the circle in the ring. Now do notice, let me just put cyclohexane over here for a second. Remember cyclohexane, we came along here and we said, we looked at this carbon and said it had 2 bonds, so we put 2 hydrogens on each carbon, right? We're not doing that over here. We look at this carbon, we go 1, 2, 3, there's only 1 hydrogen. This carbon, 1, 2, 3, only 1 hydrogen. So the molecular formula of benzene is C6H6. It's only 1 hydrogen per carbon. It's aromatic. Like I said, this is a carcinogen. Not that all aromatics are carcinogens, but this one is. So if you look at a list of carcinogens, the Center for Disease Control, I think, maintains a list of known carcinogens. It puts chemicals up there. And then it has another list of, what's it called, that list? Suspected carcinogens. Okay, it hasn't been proven, but there is some evidence to suggest that rats get cancer from this, or this gets cancer from that, and so they put the chemicals up there on a list of suspected carcinogens. I'm not exactly sure what they use the word suspected. Yeah.
So that one with the 2 hydrogens, that's
cyclohexane. Yes.
so that's how can we also differentiate between the 2, because one will have only 1 hydrogen and the other one will have 2.
Yes. And sometimes you're not, Alejandra, you're not trying to differentiate, you're trying to draw it correctly, okay? I can give you the name, cyclohexane, and you need to draw it like this. So this is cyclohexane. Right. All right, so we're just right back to our rule. Carbon's got 4 bonds around it.
What makes it a carcinogen?
I don't know. That's a good question. What makes it a carcinogen? I'm not sure. It's a really good question. I just took a course on the biochemistry of cancer. But what makes something initiate cancer and what doesn't is, cancer is insidious. So it interferes somewhere. It probably interferes somewhere. It's a nonpolar molecule. It's a molecule that can probably get through the cell membrane real easily and into the nucleus and interfere with the DNA pretty easily because it's tiny and soluble in the cell membrane. But I don't know. What it hits and causes cancer is I'm sure, being studied extensively and may even be known. Okay. Ortho, meta, and para. Let's get to the molecule for this chapter. We're in chapter 11. This one is going to come up in chapter 12. This one's going to come up in chapter 15. And this one's going to come up in chapter 14. So don't worry about every one of those right now. But this one, do get a 3x5 card for this one. You should get a 3x5 card for benzene and toluene at this point in time. I wonder if I picked out, yeah, you see benzene and toluene on this chart right here? See, if I gave you the name toluene, could you use your IUPAC rules to draw that molecule? You couldn't do that, could you? So you better draw that molecule on a 3x5 card and have the name on the other side of the card so that you go, oh, that's toluene. It's benzene with a methyl group on it. Okay, now let's go off of that for a second. Yeah, this gets a little ugly. So we have, let's take our toluene. We've got a methyl group right here. And you can see now I'm writing them as CH3 groups. I'm not necessarily putting down a carbon and putting 3 hydrogens connected to it. I just write it as a CH3 group, which is fine. But let's say we had another CH3 group right there. Let's say we had another CH3 group here. Let's say we had another molecule that had a CH3 group right here. Now I'm going to draw another, let me just draw another one right below this middle one. And here's where you got to use a little mental gymnastics. Okay, all I want you to see here is that this and this are the same thing. Okay, imagine picking this up off the board and rotating it 180 degrees and laying it right on top of that. It would lay right on top of that, wouldn't it? So if I had a benzene ring with 2 methyl groups on it, these are the 3 configurations, the only 3 configurations that they could be in. Because this one is not a 4th one, it's the same as that one. Okay, you with me? This means yes. Okay, everybody with me? So I'm going to erase that one, because it's not different from that one. These are the only 3 different compounds with a benzene ring with 2 methyl groups on them. And we don't even really call this, we wouldn't even really call this 1,2-dimethyl benzene. I guess you could call it that. But that's what you would call it if you were just going off of, it'd be 1,2-dimethyl benzene, right? That would be 1,3. There's 1, 2, 3. Be 1, 4. 1, 2, 3, 4. With me? Okay, now on the next slide, I think it is, there's let me get rid of that 1, 2. We tend to use something else here. Where is it? Yeah, we got this ortho, meta, and para. So this is the ortho position. This is the meta. So this is the ortho. Meta position, M, or the para position, P. So, yeah, with 2 methyls on there, we actually call it xylene, but I guess this could be called ortho methyl toluene, meta methyl toluene, and para methyl toluene. Ortho, meta, and para. It's saying Okay, toluene has a methyl group on it. Para-methyltoluene has another methyl group on it, directly opposite on carbon number 4. So that this position right next to carbon number 1 is the ortho, 2 away from it is the meta, 3 away from it is the para.
Is there another way of naming it? Is there another way of naming it? It's not using 1 for that.
Yeah, it could be 1, 2, 1, 3, 1, 4. Yeah, I just want you to, if you see an aromatic with an O, an M, or a P, you need to know it's going into this system here. And let me give you a way of learning that. So this is ortho, meta, para. What is that? That's a foot. Stomp. Okay? S-T-O-M-P. If you want to remember this, you can use that picture. Stomp on this. You got the O-M-P position. Stomp. This is ortho, meta, and para positions. Okay, I didn't want to, all I want to do is you to know that. So well, let me just give you give me a compound. We got the stomp. Let's say I said draw meta-chlorotoluene. Go ahead and draw that. Meta-chlorotoluene. Start out with toluene. Meta-chlorotoluene. So right down here, you're going to have a chloro group. Okay? And that's what you might see. You might be reading the paper and they say, you know, this is a carcinogen. Meta-chlorotoluene. Orthochlorotoluene isn't. Parachlorotoluene isn't. But metachloro is very toxic. That's what they're talking about. I just made that up, so don't quote me on that. I'm just saying, for instance, if you were reading down through that list of carcinogens and came across a meta or ortho or an O or an M or a P in front of something, you say, oh, that's going off the aromatic. Okay, now here's another one. Let me straighten this thing out here. I'm going to straighten this molecule out. So we've got this double bond. It's 1, 2, 3, 4, 5 carbons long. And on the 1, 2, 3, 4, on the 4th carbon here, we have a benzene ring. Okay, so that's not a benzyl group, that is a phenyl. Phenyl. So when a benzene ring is attached as a substituent, you remember all of your substituents end in YL. Methyl, ethyl, isopropyl, butyl, tertiary butyl, phenyl. We now have phenyl. And that's what you call it when there's a benzene ring as a substituent in an organic compound. Phenyl. So, and that's on there. See that down there? It says, you got another substituent, it's called phenyl. Keep this sheet. This is handy. This will be handy for the exam 1, it'll be handy for the final exam. For exam 2, we'll go over chapters 13 through 15 and the final. Okay, just know there are heterocyclic aromatic compounds. What do you mean by that? Hetero, more than one atom in the ring, more than one element. Benzene has more than one atom in the ring. It has six atoms, but they're all carbons. These are heterocyclic. This is a pyrrole ring, 1, 2, 3, 4 carbons, and a nitrogen. Pyrimidine, purine. We get into these when we look at DNA and RNA. You don't have to memorize those. Just know what a heterocyclic, what that term is talking about. It's talking about an aromatic compound that has carbon and something else in it. Okay, the only reaction of aromatics, and then I think we're done with chapter 11 and we'll take a break, is halogenation. Boy, this thing keeps coming up. Halogenation. And just real quickly, this is like halogenating an alkane. It is a substitution reaction. We're back to another substitution. It's got a double bond, but the chlorines don't add across the double bond. This is an aromatic system. And so a hydrogen is going to come off and a chlorine is going to take its place. And you get chlorobenzene plus HCl. This is a catalyst. Iron chloride catalyst. And that's the only reaction. There's, at the end of chapter 11, there's a bunch of reactions. We'll look at them right now, I think. But that's, so whether this would be bromine or iodine or fluorine, proceed the same way. You'd get one halogen on the aromatic ring, and you'd get a HF or HI or HBr. Okay, reaction summary for chapter 11. Here are your 4 addition reactions. Hydrogenation, hydration, hydrohalogenation, and halogenation. Oh. There should have been, I thought there was a slide here that summarized the reactions at the end of the chapter. I'll see if at the end of chapter 12 we have that. Now we're going into alcohols, chapter 12. Okay.